hey, this is section 3.1. Going back, Throwback Thursday.
Thursday.
We're recording this on Thursday,
TBT.
and hopefully you're watching this on Thursday. To exponential and logistic functions. And so let's start off with a little exponential function. This is standard formish.
This is a standard formish of exponential, and the big trick on an exponential as opposed to anything else is where the x is located. So as long as that x is located up in the exponent part,
x is in the exponent.
You got yourself an exponential equation.
There is actually the one other thing that has to be true, right? The base has to be a number.
Oh, yes.
Okay.
Yeah.
The base has to be a number.
We don't want to have x to the x power. That's
right. That doesn't work.
That's awkward.
And the there has to be a variable in the exponent. So let's look through on, well, for one thing, if there's a number that's multiplied in front, that's going to be your initial value.
Right.
Because if you plug a 0 in,
you just get 0.
Yeah, no matter what these numbers are, if we put a 0 here, anything to the 0 power is 1,
right.
Which gives us a. So that number, if there is 1 in front, there's not always. If there's a number in front, then your initial value is that number.
Right.
If there's not a number in front, your initial value would be 1, right? Because that's what would
that's
secretly be in front.
Yeah, if it just says b to the x, then how many b to the x's are there?
Just 1. Okay. So example 1, are the following exponential functions? If so, state the initial value and the base. If not, explain why not.
No.
No as in you're refusing to do the problem, or that? Oh, no. It's no. X to the 8th is not.
And I refuse to do that problem any further because it is not exponential.
But it says explain why not.
Because the 8 can't be up there. If 8 and x were swappies.
Right. So there's 2 reasons, and you could put both or either, but it matters that our base is not a number. And our exponent is not a variable. Those are the 2 reasons there.
Yep.
All right, what about the next one?
Next one would be an exponential equation because you have a base that is a number and an exponent that is a variable.
Okay.
And by definition, that is an exponential function.
So what are the initial value and base?
The initial value would be a 1. There's 1 times
1 times
3
3x.
to the x.
Yeah,
Yep.
1 times 3 to the x. And then
and
our
my base would be a 3.
Okay. Okay, how about...
No.
No?
No.
No. There's a lot of things that are wrong with this.
Let's just start with the fact that you have a variable for the base, and that's just no deal when you're dealing with exponentials.
Okay. And what's the other issue?
The other issue is that you got some sort of wacky square rooty situation up in the top, which is also awkward.
Yeah. So even if this was like a 5 for the base, it still wouldn't work because we can't have a random square root in the exponent.
Yeah, you could have like 3 times x in the exponent.
You could.
But
you can't have like some kind of a function happening inside of your
function.
Like you can't have sine x as your exponent.
Probably not.
No. Okay.
I don't think that would be exponential.
Yeah.
Because that would bounce around all over the place.
Right.
Right.
Okay.
Okay, good talk.
Example 2. Compute the exact value of the function for the given x value without using a calculator.
Oh, no calculator.
I know, it's terrible. Whatever will we do?
Solve it.
Okay, so we're putting a 0 where x is. So 2 times 4 to 0. Hey, it's super important here that we remember our order of operations.
I mean, super does not...
Exponent
first
comes before multiplication.
Yes. And just a point of clarification.
Okay.
The only thing that has an exponent on it is the 4.
Right.
Okay, just check.
This is 4 to the 0
times 2.
Yeah. So what is 4 to the 0 power?
It's 1.
Right. And we discussed that in the first example.
Yes. Anything to the 0 power is 1.
Anything ever.
Great grandma to the 0 power
is 1.
It's 1.
Okay. 2 times 1.
Everybody knows it's 1.
2.
That's what I said.
Okay, so that's our answer. Let's try another one.
Let's do
4 times 2 to the x, and we're going to put -3 there.
Oh no, a -3.
Well, let's review what we do with negative exponents.
Let's do.
We move them, if they're on top, to the bottom. If they were on bottom, we'd move them up to the top.
Indeed.
So this should be, the 4 is, it's fine. It doesn't have to move.
Again, point of clarification.
Yeah.
Where is the -3?
Just for the 2.
Just for the 2. Just the 2.
Okay, so the 2 cubed gets moved down to the bottom.
Right.
I know what 2 cubed is. Do you?
8.
It is 8 because it's 2 times 2 times 2. 4 over 8, we can simplify.
I know what that is.
Yeah?
Yeah. Do you know what it is?
I do.
Okay, let me see if you're right.
Okay.
Oh! Man, that was really close. I almost knew what it was.
Okay. And last, -3 times 7 to the 1/2 power.
I'm going to guess here that just the 7 has the exponent on it and not the -3.
Not the -3. Do you know what a 1/2 power means?
Yes.
Yes?
You want to write it down and see if I guess it right? That's exactly what I was going to say.
Right. Of course it was. So a 1/2 power means the square root.
Square root.
Those are the same.
1/3 would be cube root.
Cube root. Whatever number's on bottom, that's the root. Whatever number's on top is the power. So we could have like 2/3 and it would be a power of 2 and a root of 3.
Right.
But this here.
That's what we're done, by the way, because we're not using our calculator.
Right.
And square root of 7 is not something that we keep in our back pocket.
Nope. Not in my back pocket.
Not mine either.
Okay.
There's nothing in mine right now at all.
Okay.
Yeah.
Example 3. Determine formulas for the exponential functions f and g whose values are given in the table below.
Did you say f and g?
I said f and g.
Okay, all right. Just making sure.
Thanks. So let's start with f of x. So what we need for writing a rule like this is we need the initial value.
Yes, that's when your x is 0.
Right. So for both of these functions we're writing, we're going to need this value right here. That's the number that's in front. That's the a.
Right.
Okay. Then the base, the b, ends up being what we multiply by to get each step of the way here.
We're multiplying by 2.
Right. From 5 to 10, you multiply by 2. Do another one to check. 10 times 2 is 20.
From 5/2 to 5 is by 2 because the 2's cancel.
Right. And so that's what our base is whatever we're multiplying by. Because
that's
what we're
really
doing
easy.
is like whenever we have a 1 that we put in, that's 2 to the first. When we put a 2 in, that's 2 to the second. All we did between those was times by an extra 2.
Right.
So that's F. Let's try G.
G. Oh, G.
So the initial value is 9. And then this one's maybe a little bit trickier. What do we multiply by?
I know. This one looks weird.
Yeah.
But you're multiplying by 1/3.
Right.
When you divide by a number, you multiply by its reciprocal. And in this case, we actually need the fraction answer.
Right. So that's 1/3 to the x. And it's really mathematically correct to put that in parentheses. You're saying all of that is to the x power.
Right. Not just the 1 and not just the 3.
Right. And so this brings us to, at the bottom of your page, you have this exponential growth and decay box. And it says, given an exponential function, and that a is a positive number, if b is greater than 1, the function is increasing and is exponential growth. If b is less than 1, then f is decreasing and is exponential decay. So these are things that are like real life kind of things.
Yeah, real life indeed.
Yeah, we will
half-life and double life.
Yeah, we'll talk about all kinds of things throughout this chapter that either have exponential growth or exponential decay. So like what you just said with half-life,
it's not the game.
They're not the game, no. Like with radioactive substances, they those radioactive parts of it decay at a certain rate, exponentially.
Right,
so that's
exponential decay. And bacteria grows exponentially.
Unfortunately,
unfortunately. Yeah, some of them grow really fast.
Yeah, okay. I don't know Okay. So if we wanted to, we could say, hey, this one is exhibiting growth because the b is greater than 1. B right here is greater than 1. Here, b is less than 1.
Decay.
So that would be decay.
Yep.
There's probably going to be other examples.
I think there will be.
Example 4, the standard graph of an exponential function, where we have like b to the x. In this case, we just have a 1 in front of whatever's going on. If b is greater than 1, here's what's going to happen. This is exponential growth.
Exponential growth. And here's how fast exponential growth grows. For example, if you start with 1 foot off the ground on the x-axis, just like you're making this mark right here. Okay,
yeah.
1 foot off the ground straight up. And let's say we have just a base of 2. So let's just say we're graphing 2 to the x.
Okay.
By the time you move 24 feet away from where you started, your altitude would be in the vicinity of the moon. That's how fast exponential growth grows.
That's pretty crazy.
No lie.
So to the right, this graph is going to start going up at a reasonable-ish rate, and then just
and then just like a
shoot
rocket
up.
shoot into space.
And then to the left, what happens is it gets closer and closer and closer. This is actually kind of a terrible graph.
But it never hits zero,
never
but it
hits
gets really
zero.
close. Yes.
So this could end up being, like he said, this could end up being like 2 to the x. We could be talking about 3 to the x.
We could be talking about e to the x.
E to the x, because we're about to start logarithms, so e's are going to start showing up. So, or if we really want to get crazy, we could do pi to the x.
Slow down that craziness. Whoa.
But this that we're about to do, this analyzation, it should be really similar for all of these things that have some number bigger than 1 to the x power. So domain, we can plug anything we want in.
Anything we want to.
So all reals.
All reals. Negative infinity, positive infinity, all reals, capital R, whatever.
Not all reats, which is what I initially wrote. Sorry. Range is...
Now you have to pay attention here, because you're either going to be above or below the x-axis.
Right.
So that tells us where our range is going to be.
Yeah, because we aren't actually going to ever get to 0. We're just going to get close to it. So we'd need parentheses 0, since it's not ever going to equal 0.
Right.
And then it goes up forever.
Forever
until it gets
and
to
ever.
Infinity.
Yes.
Continuity. This is continuous, because
Totally
you can draw
continuous.
it without picking up your pencil.
Right. Continuity.
Okay, the symmetry.
No, there's no symmetry here,
symmetry.
because it's out of whack.
Is this bounded?
It is totally bounded below, because it never falls below the x-axis.
Right.
Or if this graph were to move up or down, it hits that floor, and it just doesn't go through the floor.
That it's not going through.
Yeah.
Extrema.
No extrema on this. Extrema would indicate that we have peaks or valleys or mountaintops or
whatever you want to call it. Basically a point where we're going from increasing to decreasing.
And that is not happening here.
Which, by the way, that's not listed here, but is it increasing or decreasing?
It increases from negative infinity to positive infinity. It does not ever decrease.
Yeah, and that's part of why there's no extrema, because extrema happens when you go from increasing to decreasing.
Yes.
Asymptotes.
There is an asymptote at y equals 0, because it puts that infinite, when you look at negative infinity, there is a limit there of 0, which indicates a horizontal asymptote.
That's right. So in behavior
would be infinity, because
the in behavior as x is going to negative infinity, right, is that's the one we want, right?
Right there.
Or do we want both ways?
Well, if you go towards negative infinity, that's your horizontal asymptote. So, which would be 0. So I think in this case, our in behavior, it's okay to look at the side that's going up.
Okay. So when we go towards negative infinity, it's going towards 0. When we go towards positive infinity for x, we're going towards positive infinity.
Yeah, that's it. That's how it goes. And so the decay function is almost this exact same thing, but in flippies.
Yeah, so our initial value here is 1 again, but this time we're going to get closer and closer to 0 this direction.
Right.
And we're going to go up and up and up, go in this direction.
And way, way up.
So in this case, because b has to be less than 0, we could be graphing things like 1/3 to the x.
Right.
So here's what they'll do sometimes, by the way. Instead of writing 1/3 to the x, they could tell you that this is 3 to the negative x.
That's the same thing. They could. Or they may even say 1/3 to the x, which looks a little bit weird, but again, it's the same situation.
Yes, because if we rewrote 3 to the negative x or 1/3 to the x, we could rewrite it in this way that shows that b is actually less than 1.
Right.
So the domain, again, is all reals.
It's all reals. We can put whatever number we want to into the exponent area.
Yeah. Our range is still 0 to infinity.
Yes. Because we're above the x-axis. We're still continuous. We still have no symmetry. So all of that is the same.
And we're still bounded.
We're still bounded below, because again, we don't fall below the x-axis. We still have no extrema, because there's no place where our function increases and then changes to decreases and then changes to increasing again.
But what about, where is this increasing or decreasing?
Well, now as you move from left to right, what is the value of y doing? So as you start on the left and you move to the right, it is decreasing the whole entire time.
Okay. And so
the asymptote again would be y equals 0, because the limit now this is where we look at that limit going towards positive infinity. The limit towards positive infinity is going to be 0. Okay, the limit towards negative infinity will be more of our in behavior situation. But this limit right here would be 0, or no, this
So
limit
where
right here would be
negative
positive
infinity,
infinity.
and then the other one
Right.
is 0.
0.
So that's analyzing some exponential functions for you.
Yeah. Yarr.
All right, so it's been a while since we've talked about transforming graphs, it feels like, so we're just gonna transform a whole bunch just real quick so that
Real
we can
fast.
remember what exactly happens.
This doesn't need to be hard, by the way.
It doesn't need to be, but you will have to refresh your memory.
Yeah, it'll be a refresher.
If our original function is y equals 3 to the x, we're going to apply each of these translations to it, transformations, I mean, and we're only going to apply that one thing.
Oh, we're not going to build.
We're not going to build.
Okay, sounds good.
So a vertical stretch of 5 is going to multiply your function by 5. If it's a vertical stretch, it just multiplies outside your function, and our function is 3 to the x.
Right.
So if it's a vertical shrink, we still multiply by whatever it is.
Right, because it's vertical.
Right.
Vertical is outies.
Okay. If it's horizontal.
That goes inside.
Okay. If it's a stretch of 4.
It's a reciprocal.
Then we do 1/4 x. Inside of our function here is the
where the
exponent.
x is. Yeah, where the x is. Not the 3, it's the x.
Right. Another way you could write this is 3 to the x over 4.
Right. Both of those ways will be shown in your book, so be comfortable with both.
Yeah. So if I want to horizontally shrink by 1/6, that's in my exponent, I'm going to multiply by the reciprocal, which is 6. So that's 3 to the 6x. Reflection across the x-axis.
Negative.
Where?
Right in front of the 3.
Okay. Because here's how this works. If we're reflecting across the x-axis, we don't make x negative.
No.
When we reflect across the y-axis, we do make the x
That is
negative.
correct. Everything you just said is 100% correct.
Okay, so that's the difference between which axis you're doing. I don't know why this is underlined, but let's just we're
going to run with it.
So if it's shifted left 2, that's a horizontal shift, so that needs to happen in our exponent, and it will be super opposite society.
Yep.
Super secret society. So left 2 is normally left would be negative, so it's plus 2.
X plus 2. And now since we're moving left and right, we're going to actually manipulate that x guy. Just a little wee skosh right here.
Just like that.
Just like that.
Okay.
So this will be
Right
x
5.
minus 5.
Right. And if we shift up.
Back to horizontals, so that's to the
No,
whole
you mean
thing.
vertical.
That's what I said.
Yeah, okay.
Yeah. Why are you arguing with me?
I'm not.
I don't like your tone of voice
Up.
right now.
Up 3.
Up
outside.
3 indeed. Totally outies.
And then down 4.
Minus 4.
Minus 4.
There you go.
So that's all of the different ways that we can translate individually. You could combine some things
You could have
together.
a total smash up of those puppies.
Yeah, but you really need to be getting comfortable at some point with how do you draw like 3 to the x? Well, you start at 1, you go up to the right, and you go down to the left.
Yes.
Closer and closer to 0. So now if I asked you to vertically draw something where you vertically stretch by 5, it goes up faster.
Goes up faster, falls down quicker.
Okay, and if we reflect it across the x-axis, we should be able to do that. That's the case where it would actually be down here, reflected across the x-axis.
Right.
So we need to be able to draw it initially, know what this looks like. If nothing else, plug in values, right?
Right. You can always just check a few values to get a good eyeball on it.
And then apply a transformation and see what happens.
Right, indeed.
All right, let's apply what we just did.
Okay, let's do it. I know exactly what 3 to the x looks like.
We actually just drew it like just a moment ago. So what does it look like?
A little cross the x-axis at 1 action there, and the y-axis at 1.
The y-axis
The y-axis at 1. We're going up z's on the right, down z's on the left, but not crossing the x-axis. So we're getting close, but not touching close. No, don't touch. Don't touch.
I didn't touch it.
Now we're going to go 3 to the x plus 4. Well, since we're actually messing with the actual x, that moves us horizontally. So instead of being where we're located, that where we cross that x-axis part will be moved to the left 4 units.
Because it's
because of
it's
the
in the
plus
exponent,
4.
It's the opposite.
Yep,
of what
super
you think.
secret
Shift
opposite
left
society.
4.
Mm-hmm.
So this 0.01 needs to actually be over here now at -4. And then the rest of it is just, it's gone.
There you go. There it is, right there.
Up that way.
And there you go.
Okay, let's try another one.
Okay, let's do e to the x. E to the x is one of those naturally occurring numbers that some famous mathematician was able to get his name onto.
Yeah.
Euler.
Yeah. Good guy.
Thinking of
sometimes.
naming a number after myself called the Hazel-Calc number.
Okay.
The number 1, because I'm number 1.
Good luck with that.
You don't think it'll work?
I don't think you'll get anybody to call it that. All
We'll
right.
see.
It still starts at 1 because we still have 1 times e to the x happening. Our
Right.
initial value is still 1. And it's actually going to be really, really similar to 3.
In fact, you probably won't be able to tell a difference.
Because e, actually, if you type just e into your calculator, is 2.7.
2.7 something,
blah, blah,
something,
blah,
something.
blah,
It's like pi. It's a non-ending, non-repeating number.
Yeah,
So,
so
hey, it looks
initially, it looks pretty similar.
looks almost identical.
So let's do some transformations.
Negative e to the 2. You put, hey, there's 2 things in there.
There are 2 things. So what about inside of our exponent? What's that doing?
That's going to give us not a stretch, but a horizontal shrink
of
1/2, or by a factor of 2.
Horizontal shrink of 1/2, and the negative in front is a reflection.
It's going to reflect you over the x-axis. So if we have a horizontal shrink, we're squeezing it like this, which means it's going to grow like this.
Okay. So this 0.01 is going to be down here at halfway to 1, right?
Right.
Is that right?
I believe so, because it would...
No, it's a horizontal shrink. Horizontal means
left to right. No, so it still goes at 1.
So what happens at 0 stays.
What happens at 0 stays at 0.
And so, but then as we go to the left, we're still getting closer and closer and closer. And then as we go to the right, it actually is going to, every point is going to move halfway to the y-axis.
Right.
Right?
Right.
So it actually goes
grows
up faster.
quicker.
Because horizontal shrinks often look like vertical stretches.
That is correct.
So
often look that way.
So there you go.
All right. Good talk.
Example 7. Graph the function, find the y-intercept in the horizontal asymptotes. Now, would this be something you'd expect them to just graph without their calculator?
Maybe not right away, but
Maybe
hopefully
not.
At some point, yes.
At some point, you should be able to kind of get used to it.
Get a shape idea.
So, graph this on your calculator. And it should look like...
Where'd our calculator go?
It's right there.
Oh, hey.
A logistic function, is it going through 1?
It's going to go through, well, in this case, it won't go through 1. Because when you're at 0, it's going to go through 12 for this one.
When you're at 0...
It'll go through 6. It'll go through 6.
It'll go through...
6.
4.
Because 12 plus 1... Yes, 4. That's what I said. I said 4. 1 plus 2 times 0.8 to the 0 power.
This is 1, so
right.
1 plus 2 is 3, so
12
4.
divided by
At
3
0,
is 4.
it's at 4.
So, yep. Now, one thing about this function is it has what's called a maximum capacity or an upper limit, which is going to be that guy right there, 12. So this graph will approach but never touch the number 12. Okay? This graph will on the right. And this graph will also approach but never touch 0 on the left.
So is that an asymptote?
It's got like a hoochie coochie shapey thingy.
Is it an asymptote?
I believe 12 is a safe asymptote to say
okay.
here, yes.
So what happens is it's got an asymptote at 12. It's similar to an exponential function that has an asymptote at 0. And then between those two things, it looks like an exponential function until it starts getting leveled off there.
Right.
And we talked about these way at the beginning of the year when we did all of the parent functions. That's not a perfect graph.
No, but that's a good shape of what it looks like. So
so graph it on your calculator and see what it looks like there. You may have to do a different window so that your window goes all the way up to 12.
Right.
But it should look kind of like that. The y-intercept we found by plugging in a 0 here.
Right,
The
that part
y-intercept
wasn't hard.
is 4.
Right.
The horizontal asymptotes come from, since it's not being shifted up or down, like there's no like plus out here.
Right.
There's one at 0, and then there's one at the upper limit,
which is 12.
12.
And that upper limit will, on the logistic function, whatever number's in the numerator will be your upper limit.
Yeah. So here's a little box that has some info about logistic growth functions. All of these things, A, B, C, and K, are positive constraints where B is less than 1. A logistic growth function in X can be written in this form that we have here. And so they said B is less than 1, so if you have a number like we did, 0.8, that's less than 1. But they could put an E in there instead.
Which is bigger than 1.
Which is bigger than 1.
But so you have to account for the bigger than 1.
By putting a negative in the exponent. So
these are excellent equations for modeling population because honestly, populations can typically only survive so long until they've reached a maximum population.
Right.
Like they can only sustain themselves. Or
it takes care of the exponential part, but then there is a place with populations where you can't get any bigger.
Or like if the super flu is going around, like swine flu did a few years ago, only so many people can get that, and then you just run out of people, and the logistic function is a model for that as well.
Exactly. Hey, example 8.
Population growth. We were just talking about this.
Yeah.
OMG.
But in this case, we are talking about some populations that will have exponential growth, at least as far as we are
for what we're looking at.
Because sometimes with models, actually what happens is you only look at like
5 or 10 years at a time or something.
Yeah, because it's really accurate for maybe a certain period of time, and then as you go on, it becomes less accurate. So we have this like
PB&J
kind of formula thing that the P0 is your initial population.
Anything 0 subscript will be an initial.
Yes, so P stands for population. So initial population, B is a number that represents the rate of growth, and T is the amount of time, usually in years, since the initial population. So on example 8, using the data in the table and assuming the growth is exponential, when would the population of Columbus surpass 800,000 persons?
Let me get my calculator.
Okay, so what we need to do is actually figure out at what rate we're growing first, right?
Yeah, fine, great.
So we have an initial population. Wow, you just knocked my armor out.
I'm sorry about that.
The initial
I found food on my
population
desk too.
is 632,910 because that's the first year they give us. And so we're saying that 10 years later, it is 711,265. This is something we know. So if we use this formula, P of T equals P naught times B to the T, we actually know almost all of this information. We know that P of T, which will be P of 10, is 711,265.
I know P naught.
Yeah.
632,910.
Okay. We don't know B. That's what we're trying to find, but we know that this is all happening when they're 10 years apart.
Right.
So we can solve for B.
What?
We can.
Let me just punch this into my calculator real quick.
Divide both sides by 632,910. I'm going to move my work over here.
Yeah, go ahead. I'm still typing in these really long numbers. Oopsie.
It just gave you a fraction.
It did, which was exactly what I typed in, so that's always good. 1.1238.
Okay. More decimals, the merrier, right? The more accurate
on this
it'll
one,
be.
yeah.
So B to the 10th is this. So how do we finish solving this?
Gosh, here's what I would do.
Yeah.
I would graph B to the 10th.
Really?
Mm-hmm.
And then
I would graph 1.1238.
And then
I would see where they intersected.
Okay.
What do you think?
Okay.
Okay. So let me just do that real quick. You can graph anything. Right?
Right.
So.
And we will talk in a later section about how to do this algebraically.
I'm actually going to graph
x to the 10th
minus 1.1238. Yeah.
And then you're looking for where it crosses the x-axis.
Yeah.
Which a lot of times is easier to look for. I thought I'd see if I could beat you, but I'm not going to. Okay, so
what's the question?
It asks we need to find B so that we can figure out where it surpasses 800,000.
Geez, this looks like it's going to be close to 1. So I'm going to analyze this graph. I'm going to find a 0.
Find a 0. And you want to find the positive 0 because there's one over there on the negative as well. B equals.
It says 1.01, but I feel like we should get a better
approximation
than that. So I'm just going to change some settings on my stuff real quick. No, I had it. Oh. I'm gonna beat you. $1.01174. Oh yeah.
I have no idea what your calculator on your computer. Oh, okay. Look, see, there's the graph. And then if you find this 0.
That's a differential equation on top, on the bottom there, kids.
So
the general solution to a differential equation.
Good times.
Slope
So that
field.
0 he found using second trace to go down and calculate a 0, and then left bound, right bound. Oh. Guess. Yep,
Thanks.
1.01174.
That's why did you doubt me?
I didn't. I just thought I'd see it through. So our model is P of t equals P naught, which is 632, 910, times 1.01174 to the t. We want to figure out when does that equal 800,000? Or when is that greater than or equal to 800,000?
So what I'm going to do is I'm going to graph that. And I'm going to graph 800,000.
And see where they...
Or graph that minus 800,000.
Right. We're trying to say that this number right here has to be greater than or equal to 800,000. And so to do that, we can do the left side minus that side and find ourselves a nice... What do you call those? Intercept?
Yeah.
A nice x-intercept.
And... I have to change my window here a little bit.
That can happen because we do have some really big numbers here.
Yeah, so I'm just going to zoom out a little bit. I'm zooming out. Oh, there it is. So, wow, this is quite a far ways out there.
Like, what should our x be? Like,
You know,
50?
probably in the 30 to 50 range, yes. Actually, 20. 20 is where it happens.
So I stuck my x
20.07
value
years.
at 50, and so whatever that is.
Right, 20.0729.
Okay.
That's how many years it's going to take. So basically 20 years.
So our answer would be about 20 years.
Yeah, about 20 years.
And a lot of times you'll see answers like that with population and things like that they'll say, oh, well, it's about this many years.
Yeah.
Because a lot of this was approximating.
Right. And you're not going to say it's going to happen in the 20th year in the month of April.
You could, but you don't actually really know. You're not that certain normally whenever you're doing this
It'll
stuff.
occur during the 20th year.
Right.
Yes.
So that's all there is to 3.1.
Really?
Yeah.
All right, good talk.